but it is all around us as a background to the natural world.
Okay, take out your reference tables, take out your notes. So it's a little confusing there because ionization is when an atom loses electrons. So they showed that alpha can do more damage in terms of ionization. However, if this banana was an alpha gun and I was shooting you guys with alpha particles, okay, you would not be harmed because what did he say about alpha and how it travels? So like in the smoke detector, what did he say about how it travels? Just a few centimeters, right? So if I was able to shoot you with my alpha gun and the alpha particles got to you, your clothes would actually block the alpha particles. But if this was a gamma ray gun, that would go right through your body. So gamma rays are much worse for us than alpha. So that was a little confusing with the ionization, and he said that alpha does more damage. But then he also showed kind of like a piece of paper maybe, where the alpha hit it and then bounced off and kind of had the disoriented look on his face. And then the beta hit it and then kind of hesitated, but then beta went right through. That's called penetrating power. Alpha, paper stops. Beta, you need some sort of foil, like aluminum foil would stop beta particles because they're small, really small. They're like electrons. Gamma, does anyone have an idea of what substance we could use to block or absorb gamma radiation?
Lead.
Yeah, lead. Kind of like X-ray. If you ever get an X-ray on some body part or at the dentist, they cover other body parts with like a lead vest, right? To protect your organs, let's say. So ultraviolet radiation, UV, X-rays, gamma rays, kind of all similar. Lead protects from that, all right? So the concept here, if you go to table O, actually I was going to pull this up. Go to table O, please. Put this up here. And we can all look at the same time. There you go. Okay, so table O, if you look, has all the particles we need for nuclear chemistry. Obviously, protons and neutrons are involved because they're in the nucleus. You have alpha, beta, gamma radiation. Positron is also another form or part of radioactive equations. We're going to get into that today, hopefully. But here you can see alpha 4/2. 4 is the top number 4. That's the mass. So alpha is really big, okay, compared to beta, which is 0 for the mass. That's why paper can block it. Your clothes can block it. The air stops it. But beta is very small. It can penetrate a lot easier. So foil, and then gamma has no mass, and the bottom number is charge. So alpha is actually +2. Where have we learned about alpha before? Mr. Herodes said he showed you the experiment and talked about it. The gold foil experiment. Anyone remember the scientist? Rutherford. He shot what? What did he do? He shot alpha particles at the gold foil, right? So the alpha particles are positive, and remember Rutherford. So if this was our gold foil, okay, and he shot high energy alpha particles, so they had enough energy to get to it. The alpha particles, most of them went straight through, but some of them. Let me back up because that might be confusing some of you. The foil was only an atom thick, so the alpha could go through because it was only an atom thick. This paper is much bigger than an atom thick. So that's why I would stop alpha. So if I had an atom thick piece of paper, it would be a different story. Anyways, back to this. The concept here is this is positive, and when it came near that positive nucleus, it deflected, right? It repelled because the nucleus is positive. So that was something Rutherford proved. I'm just trying to relate something you've already talked about to help understand the new stuff. So alpha's +2. There's no plus sign, but it's +2. Beta's -1. Gamma's 0. Gamma has no charge and no mass, so gamma is basically almost impossible to deflect or to affect at all. Whereas alpha, if you had something positive, it would repel it. Beta, if you had something negative, it would repel it, right? Deflect it away. And down here, positron, no mass, and it is +1. It's literally like the exact opposite of a beta, right? 0, E -1, 0, E +1. So this table is really important to know that it's there, where to look these up, and how to look it up, right? The mass is on top, charge is on the bottom. So that's all the stuff we're going to be using here for nuclear chemistry equations. All right. Questions so far? All right. Let's take some notes here. So we already wrote down Friday, kind of over here, nuclear chem, and then the first thing we wrote is the most important. Unstable nuclei. I don't know how I worded it, but unstable nuclei emit radiation in an attempt to become more stable. That's the overriding theme here. Okay, so unstable radioisotopes. What's a radioisotope? It's an isotope that is radioactive. So that's the first thing we wrote, and that's important. I'm going to add something to that. Okay, so the unstable isotopes emit radiation to become more stable. Why are they unstable in the first place? So isotopes become unstable, or I could just write isotopes are unstable. Become sounds like they kind of turn into something. They were already unstable. They're created naturally that way, but that's okay. Isotopes become unstable, parentheses, radioisotope. What's going on? Did I do something wrong? Isotopes become unstable. Those are called radioisotopes. A radioisotope is an isotope that's radioactive, so radioisotope. And we're going to list a whole bunch of them today. And reference tables reference table N is going to be useful. We'll come back to that. So isotopes become unstable, radioisotopes, when the nucleus has a neutron to proton ratio that is greater than 1 to 1. If it's 1 to 1, it's stable. If it's not 1 to 1, it's more unstable. And the further away from that 1 to 1 ratio, the more unstable it becomes. Let me give you an example. So unstable and then stable, just so we have an idea of what the heck I'm talking about here. So unstable, I'll do the stable first. So actually, if you're writing it down, you're listening, paying attention, and of course everybody is, who can give me one element on the chart that is stable based on what I just said here? Give me a stable nuclei. (72.5 degrees in here. It's too warm for me. Anybody? Stable means 1 to 1 ratio between neutrons and protons. I know there's someone here who can answer this question. So let's have at it. You guys are going to have to become more adventurous a little faster. We're short on time this year, so I can't wait every day for people to volunteer. Come on, let's go. Take a chance. Who cares if you're wrong? Someone give me an example. Nobody's going to give me an example. Do you know how to find the number of neutrons? Yes. The protons are easy. That's the atomic number. So someone give me one that has a ratio of 1 to 1. Max? Looks like you're raising your hand. I don't know what you just said. Say it again? Pick another one. Hydrogen has 0 neutrons, so. Helium! You're right, but that's confusing. Let's pick another one. Because helium looks like alpha, and I don't want to go down that path. Carbon! There we go. Carbon 12 is a stable nucleus. Here's why. because carbon 12 over 6, it has 6 protons and 6 neutrons. Right? You subtract them to get your neutrons. That number is the protons. 6 to 6 is 1 to 1. Someone give me an unstable nucleus on the chart. Don't take so long to do it. Pick another one. Pick a big one. A big, heavy nucleus. Big, heavy atom. Real big. Like maybe on the bottom. Uranium, that's better. Uranium, 238. So U, 238 over 92. It has 92 protons, and 238 minus 92, what is that? 146. 146 neutrons. So obviously this ratio is 1 to 1. This ratio is not even close to 1 to 1. The trick on the chart is number 84 and higher are radioactive. 84 and lower, the ones on the chart are not radioactive. And that might confuse some of you because of what I just wrote. There's this thing called the belt of stability, and I'm going to give you a worksheet that you're gonna get due tomorrow, and it kind of shows. I think it shows it. So some of the elements may not be exactly 1 to 1, but they're close enough where they're pretty stable. So they don't start getting unstable until they're really, really big. And the reason these really, really big atoms are unstable and radioactive is because the nucleus is really crowded. All right. So the size of carbon's nucleus is the same exact size as uranium's nucleus. Carbon has 12 particles in the nucleus, 6 and 6. This one has 238 particles in the nucleus. The space is the same. So imagine this room with 6 people in it versus, 12 people versus 238. Okay, 238 is kind of crowded. So radioactive isotopes don't have to be big. They don't have to be big, but a lot of times the big ones are radioactive because the nucleus is crowded. They don't like that. So they try and make room by ejecting things out of the nucleus. That's radioactivity. So this is just kind of an overriding kind of rule, but there's exceptions and it doesn't always work perfectly. Some of them aren't exactly 1 to 1, but they're close enough where it's basically stable compared to something like this. Okay? So let me give you some of those examples of the ones that are smaller. So some other smaller radioisotopes. Go to table N here, please. Table N. Everyone open up table N. I'll kind of follow here with you. If you look at table N, the second, see where it says nucleid? Top left corner there, nucleid, that just means the element, okay, the nuclei. So if you look at the second one, carbon 14. Carbon 14 is a small radioisotope. It's radioactive. Why? Because carbon 12 has a 1-to-1 ratio. Carbon 14 does not. Here's why. Carbon 14 is 14 over 6, 6 protons, 8 neutrons. It's not 1-to-1. Yes, it's close, but it's not as stable as carbon 12. So therefore, this is radioactive. Just give you a couple more. Keep going down. So you hit H3. All right, that's tritium. That's also radioactive. Keep going down. Look at nitrogen 16, N16. So it isn't always the large ones. Okay, like I said, from 84 to higher, polonium all the way up to 118, which isn't up there, they're radioactive because they're big. They have a crowded nucleus. But on table N, you see there's small ones that also are radioactive, and again, it's because of that ratio. Okay, so I'm going to stop talking about that, kind of beating it to death here, but that's an important concept. Next thing I want to show you about table N, besides the fact that it lists all those radioisotopes, which mean they give off radiation, it tells you the half-life, which we're learning in lab today and tomorrow, and we'll talk about it in class too, but lab will focus on it. And then it also tells us the decay mode. What do you think decay mode means? Earl?
What kind of particles it emits?
Yes, what kind of particle emits? Very good. If you look at gold 198, the very first one, gold 198, what type of radiation does it emit? B minus. What's a B minus? You go to table O and it tells you. Hannah, what's B minus? Beta. So the nucleus of gold 198 emits a beta particle and transmutates into something else. What it turns into, we're going to actually figure out today. What about calcium 37? Look at that third one down. Calcium 37. What type of radiation does that emit? Monique? Positron. B plus. Very good. And then if you go down to francium 220. Francium 220. Marcy, what's that? Alpha particle. Right. And just like the video said, massive, heavy nuclides tend to get rid of alpha, and then small ones tend to get rid of beta. And that makes sense. If alpha is 4/2, right? If alpha is 4, not bad. If alpha is 4/2 and beta is 0, -1e, wouldn't it make sense to you that this comes from something with a lot of mass? Because this is much more massive than this. So this would come from something like carbon 14, and look, and it does. And then this would come from something like francium 220 because this mass is way bigger, so it can lose more, right? It can lose more. It needs to lose more from the nucleus to be more stable. This doesn't need to lose as much, so it loses a smaller particle. So, you know, a lot of stuff I'm kind of saying out loud, I'm not writing. You don't necessarily need to memorize, but I'm just trying to have you make some sense of what you're seeing here, what you're learning. So table N is very useful and table O is very useful. They work together. Notice on decay mode, there isn't what? There's no example of what on that table? What type of radiation is missing? Gamma. And like you said in the video, gamma doesn't happen on its own. It's accompanied by others. So in other words, a lot of these, especially the beta decay, a lot of the ones who get rid of beta also give off gamma. They just don't show it. Okay, they just don't show it on that chart. Okay, so the most important thing to remember here is that these isotopes are unstable, so they emit radiation to become stable. That's why they do it. That's why nuclear chemistry exists. That's why radiation exists. Okay. So, and then there's your different types of radiation. We should probably write that in our notes here. So the we'll put four types of radiation. 4 types of radiation. And then we'll kind of define radiation again. You have alpha, 4/2he. We have beta, 0, -1e. You have positron, 0/1e. And then gamma, which is 0/0, and that weird looking thing. I don't know what that is. I really don't actually know what that's called. But I do want to list what I said earlier about the penetrating power. So alpha has is the least penetrating, meaning your clothes will stop that. Gamma is the most penetrating, because it's the smallest and it's high energy. Gamma's like light, travels like a wave. It can actually go through most things, whereas alpha is an actual particle. It's pretty big, so it can smack into things, so our clothes can absorb it. So that's important to remember, okay? Gamma's the smallest, it doesn't have a charge, you know, all the stuff I talked about earlier. So how would you define radiation? What is radiation? If you were going to put radiation in your own words. Laura, what do you think? If these are all examples of radiation, how would we define, you know, some little kid walks up to you and says, hey Laura, can you tell me what radiation is? I've always wanted to know. What are you going to tell that little kid? All right, I'm going to go with that. Radiation. I'm just going to add, instead of something, I'm going to say a particle or wave. That is what? What'd you say? that is, I'm going to just write emitted from what kind of atom? Good. From a radioisotope. Everything you said was good. I just changed it a little bit. So radiation, particle or wave that is emitted from a radioisotope. And I also want to note that heat is sometimes created as well. So sometimes you have heat involved too. So radioisotopes may get warm. So the radiation not only is particles and waves, but also there's heat involved with that. Okay. Okay, two or three more things I want to get done here before we wrap it up. I'll give you that worksheet. Can I erase? Yes? Okay. So, while we're talking about the types of radiation, do me a favor. And I got a little animation for this. I'll have to show you tomorrow. Draw a little box over here. Label that radioactive source. And then over here somewhere, draw a little thing with a positive sign and a little thing with a negative sign. Let's say those are electrically charged plates. So this plate has a negative charge to it. This has a positive charge to it. And this radioactive source is emitting all four types of radiation. So one type of radiation goes straight through them, appears to be unaffected by the positive and negative. One form kind of bends down towards the negative. Another one bends down here, but not quite as sharp as the other one. And then one bends up towards the positive. And then you have 1, 2, 3, 4. Technically 4 should be a little more bent closer to the negative. I didn't draw it perfect, but it's attracted to the minus sign here more than 3 is. All right, alpha, beta, gamma, positron. Which one is which? While you're figuring that out, I'm going to pass out your homework. We're not done with the notes yet, but label those numbers. Based on everything you just learned, which is which? Which is which form of radiation? This would be perfect to sit and discuss, but for the sake of time, we're going to just kind of do it individually. So that's due tomorrow. Take you like, I don't know, between 5 and 10 minutes. And there's one more thing in the notes I got to show you to kind of help you with number 64 on that. All right, let's do it. What's number 1, Bree? Which 4 types of radiation would be attracted to a positive? Positives and positives do what? Right. So we're looking for opposite. Beta, very good. So number 1 is beta. 0, -1 E, that's our B minus. That's our beta. Beta would be attracted to a positive field. Opposites attract. You know what the regents is going to say? The beta is deflected towards the positive. It's a stupid way to say it because kids think deflected. I think deflected means go away. They say deflected towards positive. So just forget the wording. If you see this question this year, forget the wording. Just know the concept. The negative will go towards the positive. What's number 2? Who goes straight through, Dylan?
Gamma.
Gamma doesn't have a charge. So that's gamma. Doesn't have a charge. It isn't affected by positives or negatives. Maddie, what about 3? Or 4?
Positron.
Which one? Yes, positron. 0, positive 1, E. That's a B plus. A plus answers up. Okay. Ariana. 4. Alpha. Pat, why is this alpha? And why is that positron?
So alpha. Positron has a positive proton, while alpha has 2 of them.
Yeah, there's more charge here, and it's heavier, so it would be deflect. The charge would really cause it to bend more than the other one because it has more of a charge. Very good. All right, so here's the moral of the story. Gamma undeflected, positives are attracted to the negative, and the negative is attracted to the positive. Last thing, I hope I have time, otherwise you're going to get confused on number 64. All right. Okay. I'm probably gonna run out of time here, but write this down. Alpha decay. Yeah, you know what? I'm gonna get trapped here. So I tell you what. You got 4 questions. That's it. The last one, do the best you can. Look it up, maybe that would help. If not, I'll do it tomorrow. I'll be after school if you need help.